Now, moving on to our next topic, which is colligative properties. We want to deal with colligative properties within our solutions because anytime you add a solute to a solution, what happens is you end up changing some properties of that solvent. Okay, so water we know has a certain surface tension, has a certain boiling point, melting point, freezing point. It has certain amounts of hydrogen bonding to it. All those properties change slightly as you add solute. If you imagine, the solute particles actually kind of block the water from doing the hydrogen bonding properly. Okay, so you imagine a normal water solution has a bunch of water molecules all intertwined and synced together by these hydrogen bonds, okay, which works out really well. As soon as we start adding solute in, so we start adding in some sodium ions or some chlorine ions, what can happen is these chlorine ions and sodium ions start to disrupt some of this hydrogen bonding. And when you disrupt that hydrogen bonding, it changes what happens to your solvent. So some properties change. Okay. Now, one thing we need to be aware of is this is for non-volatile solutes only. Okay. So volatile. Okay. If you know a volatile person, it's probably somebody who's kind of angry and kind of change very quickly. Kind of person. A non-volatile means it doesn't evaporate very quickly. Okay. So volatile solutes are things that evaporate on their own very quickly. Non-volatile means that they don't evaporate. Or another way of saying that is tendency to escape a solution. So salt would be a great example of a non-volatile solute because you dissolve it in water, it's going to basically stay in there. Okay. Ether, which is a very lightweight gas, organic gas, would be an example of a volatile solute because as soon as you try to dissolve it in water, it's just going to evaporate out very quickly, being a volatile solute. So we're really not talking about gas solutes here very much. It's more focusing on solids and liquid solutes in this idea. Okay. So one of the things that adding solute does to our solvent in terms of colligative properties is it changes the vapor pressure. So as you increase the amount of solute in the solution, the vapor pressure will decrease. Okay. So if you can imagine, water molecules have to work together to generate this vapor pressure, or basically they have to work together to push back against the atmospheric pressure at all times. So as you add solute particles in there, the solute particles mess that up. The solute particles get in the way of the hydrogen bonding. The solute particles kind of block the ability of the water molecule to generate vapor pressure. So because they block that ability, the vapor pressure of that solution actually goes down. Now the result of that is that we get two kind of key things that go from that. The first is we get a boiling point elevation, and the second thing we get is a freezing point depression. Okay. So if you think about it, because the vapor pressure has been reduced, what happens is the whole solution now needs more energy to bring the whole vapor pressure back up to a temperature at which it will boil. Okay. So if you can imagine a solution that normally has a vapor pressure of, let's say, if our solution at 100 degrees Celsius has a vapor pressure of 1 atmosphere, okay, if this is pure water, this will boil because we have at 100 degrees Celsius, what atmospheric pressure pushing down is 1. When those two things equal, we boil. Okay. Now, if I add salt in here, what's going to happen is that salt is going to disturb this, and it's going to drop this vapor pressure down, so it won't be 1 atmosphere anymore. Maybe it'll be only 0.8. Okay. So at 0.8 atmospheres, it doesn't match the 1 anymore, and it won't boil. So how do we get more vapor pressure? Well, vapor pressure is linked to temperature. So as we increase temperature, we increase vapor pressure. So the salt has reduced the vapor pressure. So to bring it back up to match 1, we got to heat it up some more. So maybe we'll bring it up to 105 degrees Celsius. And as you warm it up, this number then can go up to 1 again, and it will boil. Okay? So what happens is the addition of the solute lowers the vapor pressure of the solvent. So to get it back to the point where it needs to boil, that 1 atmosphere pushing back on it, you need to make the temperature hotter or make it warmer. Okay? So the boiling point goes up. Now, the exact same thing happens at the freezing point, but it goes the other direction. So when you're cooling something down to freeze, okay, at some point those hydrogen bonds start to lock into place and they start to hold the water molecule stationary or just so it vibrates. As a result, we call that freezing. Now, if you have salt particles or sugar molecules or other solutes in there, those things disturb the hydrogen bonding. So they're not as easily locked into place. It takes less energy to get them to lock into place. So what you really need there is a reduction in temperature. So if you can imagine, normally when we hit this 0 degree point, we start to form these hexagonal water crystals sort of shapes. That's kind of a pentagon. We start putting these crystals into shape. Well, these bonds holding it all together, those are hydrogen bonds. But if we have a salt molecule in the way here, that's not going to lock into place as much as it would before. It disturbs that. So as a result, what happens is, at this particular temperature, at 0 degrees Celsius, we can't lock these in place like we used to. So we have to cool it down even more, okay? So we got to get it even colder, so even with the disruption of this, we can still get all these particles to lock in place, even amongst those solute particles. So as a result, we got to bring this temperature down, and maybe it'll actually freeze at a negative 10 degrees Celsius instead, okay? So what happens is, you actually expand the entire liquid phase when you're dealing with colligative properties, okay? So if we take a look at this applet from Iowa State University, here's water. Here is your solute particles. So let's just kind of start. Let's add in a lot of water, and let's just start. And if we look, okay, boiling point of water is 100 degrees Celsius. Freezing point is 0. We'll get to these values in a minute. Okay, it's going to warm up. Okay, starting to see a few little bubbles as it warms up. And then once it reaches that point, or we're at 100 degrees Celsius, we will boil. So now we're at about 100 degrees Celsius, and we're boiling. Okay, so it won't change temperature here. It'll stay at 100 as it boils. So now we're boiling, particles are leaving, and that's kind of normal. However, if I do the same process, but I add salt in, let's say I add in 10 grams of salt into here and dissolve that. And now, and now I want to get this to boil, okay? Again, it's going to warm up, okay? We'll put this into a hot water bath. Notice the switch is set to hot. Normal boiling point for water is 100, but we put 10 grams of salt in. So as this thing warms up, we're at 73. We're not quite at the boiling point yet. We're getting really close, and we hit 100, but we go right past that, and it warms up even more. So if you look what's happening here, now the water molecules are trying to leave, but they can't all get out. Because if this guy's trying to leave right here, he's going to escape. Okay? No, he's not. Look, they got blocked. So it's almost like the solute particles are actually blocking the boiling process from happening. So what you need to do is give it more energy, higher vapor pressure, to get them to actually leave that process. Okay? You can do the exact same thing for cold. If we flip our switch here to cold, and now we want to freeze this, we'll set the same thing up. We have water here and 10 grams of salt in here, and we want to freeze this down instead. We see that as it cools down, okay, normally it would freeze at 0 degrees Celsius, but here we are at 3, 2, 1, and we had salt in there, so we're negative now, and it's still not frozen. So if you look, they're trying to freeze, but again, they block the process. These solute particles actually can block that process of resolidification. They basically don't let the molecule solidify again. So to get it to happen, you need to reduce the temperature even more, or expand that liquid phase between there. Okay? So when you look at that, the result of your colligative properties is that this is your pure solvent, where we have our, again, our pressure, temperature. Remember our phase diagram here, our triple point, critical point. If we switch this and we add a solute to this, what actually happens to your solution, okay, from the original to your new, is you basically move the triple point down the line further away. So as you graph it, you actually see the triple point move this direction. So you have a smaller solid phase, a smaller gaseous phase, and you've expanded that liquid phase inside of here. Okay, so that's what you look at if you actually look at the actual graph of this. It shows how this expands. So at 1 atmosphere pressure, the original freezing point was here. Now we've dropped it to here, so it actually decreased in temperature. The original boiling point was here, and now we've increased it to here. Okay, so that is what colligative properties do for us. Okay.